The cosmos has a secret about its childhood. For a long time, scientists thought the first galaxies formed slowly, over billions of years, a slow, majestic dance. But that story is breaking apart now. New observations show something different. They show galaxies assembling at breakneck speeds. They were appearing fully formed. And this was when the universe was just an infant. So we have a front-row seat to a revolution, a scientific revolution. We're uncovering why the early universe formed galaxies so fast. Faster than any theory predicted. We have to explore if the fabric of dark matter is wrong, or if the first stars rewrote the rules of creation. And what does it mean for our understanding of everything if the universe's first chapter wasn't slow? If it was written in a frantic rush? For a long time, we had this cosmic rulebook. And it made sense. It's called the lambda cold dark matter model. Lambda is dark energy, that force pushing the universe apart. Cold dark matter is the other part. It's invisible, slow-moving. It forms the gravitational scaffolding for everything. So the story of the first galaxies was supposed to be a patient one. After the Big Bang, the universe expanded and cooled. Then came a long, quiet dark age, millions of years, just a vast sea of neutral hydrogen gas, no stars. But the seeds of structure were already there, tiny quantum ripples from the very beginning. Gravity worked on those ripples, amplified them over eons. The cold dark matter clumped first. It formed huge, invisible spheres, halos. You can think of them as cosmic bowls. Their gravity carved dips into space itself. Into those wells, the ordinary gas could flow, the hydrogen and helium, but it was never fast. The gas had to cool, shed energy, condense and spiral inward slowly. It was a stately dance. Small halos formed, then merged over time to build larger ones, gathering more gas along the way. Only after that long accumulation could a halo become massive enough to trigger the collapse, the ignition of the first true stars. Computer simulations based on these rules painted a consistent picture, a universe waking up slowly. The first substantial galaxies only beginning to glow hundreds of millions of years after it all began. This timeline wasn't just a guess, it was a detailed prediction. Born from our fundamental understanding of physics and gravity, it was the established narrative, the expected prologue, and that's why the first images from the new cosmic time machines caused such a shock. The James Webb Space Telescope was built to see the universe's first light. Its infrared eyes were meant to cut through dust to find that ancient, stretched glow from the beginning. And it did. It looked back to when the cosmos was only 300 or 400 million years old. Just a blink, but what it saw wasn't faint flickers. It saw galaxies. Bright ones, massive ones, they were shockingly mature. It was like finding a teenager in a newborn's crib. Not just small clumps of stars, these were structured. Brimming with light, they looked as evolved as galaxies that had existed for billions of years. The data was wild. The star formation rates were off the charts. The calculated masses were enormous. Our models said these things shouldn't exist for hundreds of millions of years more, but there they were, clear as day in the deep field images. Not smudges, undeniable cosmic cities shining from the edge of time. That was the first great shock. The telescope's power didn't just give us new data. It gave us a paradox. It left cosmologists with a choice. Either we were misreading these brilliant, ancient lights, or our fundamental recipe for the universe, the physics of gravity, gas, and dark matter, was missing something. A key ingredient. The search for that ingredient became the great cosmic detective story of our time. Scientists had to go back and look at what the universe is made of. They started with the invisible structure, the dark matter. Our model needs it to be cold. Cold means slow, heavy. It would gather easily right from the start, making those gravity wells for gas. But maybe dark matter isn't cold, maybe it's warm. That would mean lighter particles, faster particles, moving quickly. That speed changes things. It smooths everything out on the smallest scales. It stops the little clumps from forming early. No tiny halos, but that smoothing could be important. By clearing away the small stuff, the universe could put all its gravity into the bigger structures. The massive halos, and those could then build faster, more directly once they began. It's a trade. You lose the small first pieces, but you get a quicker path to the large cosmic cities we see. There's another idea, self-interacting dark matter. What if these particles could bounce off each other, scatter, move energy around? In a normal halo, the particles just orbit in a big, loose cloud. But if they interact, they can lose energy. They can fall toward the center. That makes a halo with a much denser core, a deeper, steeper gravity well. And a deeper well pulls in regular gas much more fiercely. It could start star formation in a huge rush. So just by changing dark matter's nature from slow and distant to fast and smooth, or even interactive, we could change the whole early story. Looking for dark matter isn't just about finding missing mass anymore. It's about reading the plans for how the universe was built, plans we might have had wrong this whole time. We thought the problem was the cosmic scaffolding, but maybe it was the engine inside. Our old models assumed star formation was messy and wasteful. In a galaxy like ours, when a gas cloud collapses, the process limits itself. The first massive stars ignite, they blast out radiation and stellar winds. Then they end as supernova. That energy heats the gas, it blows it away. It scatters the fuel for new stars, so in our neighborhood, maybe 1 or 2% of a gas cloud turns into stars. The rest gets ejected. We assumed the early universe worked the same. That feedback put a hard brake on a young galaxy's growth, but that assumption might be wrong. The first generation of stars were pure, only hydrogen and helium from the Big Bang. Without heavier elements metals, the gas couldn't cool efficiently. To collapse, a cloud has to lose heat, to shrink. The first stars had to be enormous to overcome that. They were likely behemoths, hundreds of times the mass of our sun, and such giants live fast, they die young. A brief, furious flash, their deaths were cataclysmic. But here's the twist. In a metal-free universe, those first supernova might not have been destructive. They might have been the opposite, a creative spark. When those primordial giants exploded, they did something for the first time. They forged heavier elements in their cores. They scattered them across space. They polluted the pristine gas with metals, and that pollution was the key to faster growth. Metals are excellent at radiating away heat, so gas clouds enriched by this first wave could cool much faster. They could fragment into denser, cooler clumps. Think of it like making a snowball. Dry, fluffy snow just falls apart, but add a little water, a catalyst, and the snow packs together instantly. Those first metals were the water. They transformed the raw material from something that resisted collapse into something that embraced it. This sets up runaway creation. A first wave of monstrous stars lives and dies in a few million years. Their explosions seed the local gas with metals. That metal-rich gas then cools and collapses with stunning efficiency. It spawns not just a few more stars, but a whole burst of them. This isn't negative feedback, it's positive feedback, an explosion that triggers more birth, not more death. If star formation in these early halos was near 100% efficient, if almost all the gas that fell in got turned into stars in a frantic rush, then the math changes completely. A galaxy could reach the brilliant masses we see with Webb, not over hundreds of millions of years, but in just a few frantic generations of stars. The solution to the speed mystery might not be in the dark matter halo. It might be written in the explosive physics of the first light itself. A star isn't the only engine for a galaxy. There's another force, gravity itself. The supermassive black hole. We see them now, these dark giants, in the center of almost every large galaxy. And the most surprising thing is they were there from the beginning. Webb has found them, active, feeding black holes, shining in galaxies that are just infants. They grew to billions of solar masses in what seems like an instant. That raises a radical question. Did the black hole come first? Did it build the galaxy around itself? One theory points to a direct collapse black hole. In the early universe, a massive cloud of pure hydrogen. Under the right conditions, it could have collapsed under its own weight. So violently, so directly, it skipped the star stage altogether. It would have fallen straight into a black hole, a seed of immense gravity, born in one swift, silent act. This isn't a dead star, it's a cosmic shortcut. A primordial anchor, and that anchor changes everything. Gas swirls into the black hole's gravity well. It doesn't just vanish, it forms a spinning disk. Friction heats that material to millions of degrees. It glows with the light of a billion stars. It can blast out jets, particles moving near light speed. This violent energy release is called feedback. For a long time, astronomers thought that feedback was purely destructive. The black hole's fury, blowing away the gas needed for stars, putting a hard stop on a galaxy's growth. But in the early universe, in that cramped, gas-rich nursery, the rules might have been different. Imagine a shockwave from a powerful explosion hitting a vast, dense cloud. Instead of blowing the cloud apart, the intense pressure from that wavefront slams into pockets of gas. It squeezes them, crushes them past a point of no return, triggering a cascade of new star birth right at the wave's edge. This is black hole feedback, not as a brake, but as a cosmic piston. A turbocharger. In this frantic scenario, the black hole and its galaxy aren't separate. They aren't taking turns, they're partners in a frenzied dance. The black hole's fierce energy compresses the gas. It sparks a firestorm of star formation right in the galactic core. Those new stars live and die. They feed more gas back toward the black hole, which then erupts again, compressing more gas. It becomes a self-reinforcing cycle of creation, a symbiotic explosion of structure. This could explain it. How we see both brilliant galaxies and brilliant black holes so early. They built each other at a pace our old models never thought was possible. The galaxy's heart wasn't a quiet place slowly gathering mass. It was a forge lit by a dark sun, working at a blinding speed. Before we can rewrite the rules, we need to ask if we're even reading them correctly. Everything we learn from the edge of time comes to us as light. And light can lie. The whole argument for these impossibly early, massive galaxies stands on two things: their distance and their brightness. Both could be wrong. Take distance. We measure it by redshift. The universe expands. It stretches the light traveling through it, shifting it toward red. The more stretched, the farther it's come, the older the galaxy we're seeing. But what if something else is reddening that light? Cosmic dust, for instance. Dust scatters blue light more than red, so objects look redder than they are. Could a dusty, closer galaxy be pretending to be a primordial one? Astronomers have thought about this from the beginning. The consensus now, after a lot of work, is that dust might explain a few strange cases, but it can't explain the whole crowd of these brilliant, deeply redshifted galaxies. The evidence for their incredible distance is holding. That brings us to the second part, brightness. We see how much light a galaxy gives off, and we use that to guess its mass. More light means more stars, means more mass. It seems simple, but that calculation is built on assumptions about how stars work. We assume we know the recipe for a galaxy. We assume a certain mix of star sizes, a few brilliant giants, many more modest suns, countless faint dwarfs. That mix is called the initial mass function. It's the guide, but what if the early universe used a different recipe? What if back then star formation made more superstars, an overabundance of those brilliant, short-lived giants? A galaxy full of those would shine with a fierce, deceptive light. It could look dazzlingly bright, but actually have far fewer total stars and far less total mass than we think. It would be an illusion, a city that looks like a metropolis from its blazing downtown, but whose suburbs are mostly empty. There's another possibility. What if we're seeing these galaxies not in settled maturity, but in a brief tantrum of birth, a starburst, a volcanic episode where star formation runs wild, lighting up the core with the fire of a billion suns being born at once? That would be a flash in the pan, a temporary flare that makes a modest galaxy look for a moment like a titan. In a few million years, the burst would fade, the massive stars would die, and the galaxy would settle into a quieter life. We'd just have the extraordinary luck to be looking at the exact instant of its most dramatic show. This is the careful work. Before we call for new dark matter or new black hole physics, we have to put the data itself on trial. We have to interrogate the light. The answer to the speed mystery might not be finding something exotic out there. It might be realizing we've been misreading the familiar signals all along. The truth is often hidden not in what we see, but in how we choose to see it. Even light can be warped by the cosmos. Some of these ancient galaxies, the brightest ones, might not be as brilliant as they seem. Their splendor could be a trick, a natural trick of physics. They're being magnified by a cosmic lens. That's gravitational lensing. Einstein's theory predicted it. General relativity over a century ago. The theory says mass warps space-time. You can picture a heavy bowling ball on a stretched rubber sheet. The sheet dips. And if you roll a marble past, its path curves. It follows the dip. In space, the bowling ball is something massive, a galaxy cluster. The marble is a beam of light from a galaxy far behind it. As that light travels toward us, it passes through that warped region. Its path bends, but the cluster can do more than bend it. It can act like a lens. It can focus that light, take the faint glow of a distant infant galaxy and amplify it, make it appear dozens of times brighter, dozens of times larger than it really is. This is a powerful tool. Astronomers use these natural telescopes to see farther than any human instrument could. But it also complicates things. When we see a dazzling galaxy from the cosmic dawn, we have to ask a question. Is it truly that massive, or is it just perfectly positioned behind a cosmic magnifier? The calculations depend on the light we receive. The mass, the star formation rate, all of it. If that light has been amplified by a lens we don't know about or haven't mapped perfectly, then our numbers are wrong. We could be looking at a modest galaxy and calling it a giant. The challenge is that lensing isn't always obvious. A perfect, symmetrical alignment creates a dramatic effect, a ring of light around the foreground cluster, an Einstein ring. But nature is rarely that neat. More often, the alignment is partial. It distorts the background galaxy into strange arcs, into multiple, smeared images. Astronomers have become experts at spotting these signatures. They use models to map the invisible mass of the foreground cluster, to reverse engineer the distortion. They work to subtract the lensing boost to see the galaxy's true self. But there's a deeper statistical puzzle. Our searches for the earliest galaxies are surveys of the brightest objects. We're looking for needles in a cosmic haystack, and gravitational lensing makes some needles shine far more brightly. That means our sample of the early universe might be biased. We might be preferentially finding the galaxies that are being magnified, the outliers, and mistaking them for the typical population. It's like judging the height of all people by only studying those standing on boxes. The average would be wildly off, so to understand the universe's frantic youth, we need a meticulous audit of the light. Every brilliant candidate has to be scrutinized. Is its light path clean, or does it pass through a hidden warp? This careful, painstaking work is the foundation. Before we can say the rules of cosmology are broken, we have to be certain. Certain we're not being fooled by the universe's own grand illusions. The truth is written in the light, but only if we learn to read every twist in its journey. The final judge isn't a telescope, it's a machine. We build whole universes inside supercomputers. These aren't animations, they're vast simulations, projects like Illustris TNG. ERGLE, they start with a universe just after the Big Bang. They seed it with the conditions we think existed, the right mix of dark matter and gas. Those tiny quantum ripples from inflation, then they hit start. The computers apply every law of physics we know. Gravity pulls, gas cools and collapses. Stars ignite, they explode. Black holes form, they feed. The simulation runs for billions of virtual years. It's the ultimate test. If our understanding is right, what comes out should look exactly like the real universe we see. And for a long time, this worked. These digital cosmos reproduced the grand cosmic web. They built spirals and ellipticals that matched our own neighborhood in detail. It was a triumph, a validation that our core recipe was sound. But then we looked to the earliest epochs, the time of cosmic dawn, and the simulations failed. They couldn't make galaxies fast enough. No matter how they tuned the physics, their virtual infant universes stayed dim, slow to develop. They made faint clumps where the James Webb Space Telescope saw brilliant, structured cities. This mismatch isn't a bug, it's the most important clue we have. The simulations are doing exactly what we told them. They're faithfully following the rules we programmed. And if those rules produce a universe that looks wrong in its first chapters, then the rules themselves must be incomplete. So scientists are going back to the drawing board. They're creating new suites of simulations. This time, they're changing the recipe. They dial up the efficiency of gas cooling, let it collapse into stars almost instantly. They swap out cold dark matter for a warmer, faster variety. They program in those direct collapse black holes, seeding the early universe with massive gravity anchors from the start. Each new simulation is a grand experiment, a what-if scenario across billions of virtual light years. We can run the universe 1,000 times, 1,000 different starting conditions. We can watch in accelerated time which combinations of new physics might lead to those impossibly bright, early galaxies. The tension between what the simulations predict and what Webb sees isn't a crisis. It's a compass. It points directly at the gaps in our knowledge. Every time a simulation fails to match reality, it tells us where to look next, which knob to turn, which fundamental law to question. These digital universes are our proving grounds. They let us test ideas that would take billions of real years to observe. They're the bridge between a shocking observation and a new theory. The work is slow, meticulous, computationally immense, but it's how we'll find the missing lines in the universe's opening chapter. One line of code at a time. Every cosmic environment has its own rules. The space between galaxies isn't empty. It's filled with a thin gas, the intergalactic medium. For a long time, we thought of the early version of this medium as a cold, quiet sea, a vast expanse of neutral hydrogen, just waiting to be gathered by the gravity of the first dark matter halos. It was the perfect, calm nursery, but new ideas are challenging that. They suggest the nursery might have been buzzing with energy much earlier, that the intergalactic medium could have been warmer and more electrically charged far earlier than we thought. Imagine filling a bucket from a calm pond. The water flows in smoothly. Now imagine the pond is already churning and warm. The process changes completely. That's the shift. What could have heated this cosmic bath so early? The first suspects are the first stars. Those monstrous, pure hydrogen giants would have blazed with intense ultraviolet radiation. And that radiation doesn't just light up space, it strips electrons from atoms. It's a process called ionization. It turns neutral gas into a plasma, a charged soup. And that act pumps energy into the gas. It heats it up. There are even more exotic possibilities. Some theories say dark matter itself might decay or annihilate. That it could release a steady background hum of energy, warming the universe from within. So the stage for galaxy formation might not have been a cold, dark theater. It might have been a pre-warmed arena, already crackling with faint energy, and this changes the physics. A warmer intergalactic medium presents a barrier. Cool gas flows easily into a gravitational well. Warm, energetic gas resists. It has more pressure. It won't just meekly fall into a forming halo. At first, that sounds like it would slow everything down. A warmer bath should make it harder for galaxies to gather fuel, but counterintuitively, this resistance might be the secret to their rapid rise. Think of it like building a dam. If a river flows in slowly, you get a steady trickle into your reservoir. But if you first hold the water back, letting it pool up against the barrier, you accumulate a huge volume. Then when the dam is released, you get a sudden, massive surge. A warmer intergalactic medium could act like that initial barrier. It prevents the gas from fragmenting into tiny, inefficient clumps too early. It holds it in larger reservoirs in the cosmic web. Then, when a sufficiently massive dark matter halo forms, its gravity is strong enough to overcome the gas's thermal pressure. It pulls in not a trickle but a whole accumulated reservoir at once, a deluge of raw material. There's another, more direct effect. If the gas entering a halo is already ionized, it's already been processed. The hard work of stripping electrons is done, so once inside the halo's embrace, the gas can cool and collapse much faster. It doesn't have to spend time on that initial ionization step. It can radiate its heat away more efficiently and get straight to the business of making stars. So a preheated, pre-ionized cosmic environment isn't necessarily a hostile one. It could be a catalyst. It sets conditions that favor sudden, explosive growth over slow, steady accumulation. The galaxy doesn't have to patiently gather cold gas from a vast sea. It can tap into a pre-accumulated, pre-processed supply. This turns a key assumption on its head. We thought galaxies built themselves in a cold, dark void. But they might have been born in a warm, charged soup, a background condition that primed the universe for a frantic and brilliant dawn. The very fabric of space between the stars holds clues. And we are just beginning to feel its temperature. Growth through violence is another path. In our own cosmic neighborhood, we see the evidence of galactic mergers everywhere. Those tidal tails from interacting spirals, the giant elliptical galaxies we think are the end result of many collisions. This process, hierarchical assembly, is built into our models. Smaller things merge to make bigger things, but the timeline has always been in the slow billions. The early universe might have changed that schedule completely. Imagine a nursery not of orderly cribs spaced far apart, but a crowded room where infants are constantly bumping into each other, grasping, merging almost from the start. That's accelerated cannibalism. What if the first proto-galaxies weren't rare and isolated? What if they were incredibly common, packed together in a dense cosmic web? In that kind of environment, gravity's dance would be frantic. Small dark matter halos, each holding its own pocket of newborn stars, swinging past each other. Their orbits decaying quickly, pulled by mutual attraction and the drag of thick primordial gas. They wouldn't have billions of years. They'd rush together in a series of rapid, successive mergers. And each collision wouldn't just add mass. It would send shockwaves through the combined gas, triggering furious new bursts of star formation. A galaxy could grow not just from within, but by devouring its neighbors and lighting a fire with the fresh fuel. So the question is, what could make the early universe so crowded? One possibility is in the first blueprint, the cosmic microwave background. It's a snapshot of the universe at 380,000 years old. It shows the seeds of structure, tiny density variations from the Big Bang. But this snapshot is a bit fuzzy. It shows the large-scale patterns beautifully. The small-scale details, the size of the very first clumps, are harder to read. It's possible that on those smallest scales, the initial ripples were slightly more pronounced than our measurements suggest. Just a small boost in those microscopic variations would mean that, right from the start, the universe made more small dark matter halos and packed them closer together. The construction site would be flooded with workers, leading to chaotic, rapid assembly. There's another twist, more observational. Our ability to see these first building blocks depends entirely on their light. If the first star-forming halos were especially efficient, if they turned almost all their gas into brilliant, massive stars, then they would shine like beacons. We wouldn't be missing a dark, silent population. We'd be seeing nearly every single piece, and if we see them all, and they are all already shining, then the stage is set for a frenzy. Every bright knot we see in those deep web images isn't just a single galaxy. It could be a swarm of merging proto-galaxies caught in the act, their light blending into one brilliant, massive-looking source. The merger rate wouldn't just be fast, it would be the dominant mode of growth from the very beginning. This changes the narrative from a story of slow cultivation to one of explosive consolidation. A universe where galactic cannibalism starts immediately doesn't wait for slow gas cooling or patient orbital dances. It fast-tracks everything. It compresses what we thought should take billions of years into a few 100 million. Those colossal galaxies at the dawn of time might not have grown from the inside out. They might have been assembled from the outside in a relentless, violent campaign of cosmic acquisition. Their brilliance isn't just the light of new stars being born. It's the flash of empires being forged in collision after collision. The early universe may not have been a quiet nursery. It may have been the most competitive arena in history. At the start, the universe had just 3 elements: hydrogen, helium, and a trace of lithium. Everything else had to come from that. All the stars, the planets, life, but that simple mix has a problem. It's not very good at making new stars. A cloud of pure hydrogen gas holds its heat. To collapse into a star, a cloud needs to cool down, to shrink. Without heavier elements, what we call metals, it can't shed that energy easily, so the first stars had to fight that. We think that's why they were so huge, hundreds of times the sun's mass. They were brute force, but their lives were short and bright, and they changed everything. When they died in supernova, they did something new. They fused those light elements into heavier ones in their cores: carbon, oxygen, silicon, iron. They made the first metals and scattered them. That's chemical enrichment, and the idea was always that this was slow, that it took many generations of stars, over hundreds of millions of years, to spread enough metals to really matter. But what if that first wave wasn't a trickle? What if it was a flood? What if those first stars polluted their surroundings with heavy elements almost immediately? That changes everything. Think of a blacksmith. You start with raw iron ore. It's tough. It takes a lot of heat and work to shape it. But once you have a little refined steel, you can make better tools. And with those tools, you can refine more ore faster. Metals in space work like that. A gas cloud with even a tiny bit of carbon and oxygen can radiate heat away. Like a radiator, it cools down fast, and a cool cloud is fragile. It can fragment into many smaller, denser clumps. So instead of forming 1 or 2 monster stars, it can make a whole cluster of stars, all different sizes. Star formation shifts from a clumsy act of force to something efficient. A refined process. That's the catalytic power of chemistry. A little of the right element acts like an accelerator. Now take that to a galactic scale. A first generation of massive stars lives and dies in a few million years. their supernova flood their dark matter halo with new metals. So the next batch of gas that falls into that halo isn't pristine anymore. It's pre-enriched. It already has the seeds of efficiency. So when it collapses, it does so with a speed the first generation couldn't match. This creates a feedback loop, a chain reaction. More metals lead to more efficient star formation. More efficient star formation builds more stars quickly. Those stars then live, die, and make even more metals. The cycle feeds itself. It supercharges the growth of a galaxy in a frantic rush. A galaxy could go from a first, clumsy generation to a modern stellar factory in what seems like an instant. The quest now is to find the evidence, the chemical fingerprint of that frantic dawn. Astronomers are using the James Webb Space Telescope not just for pictures but to dissect light. They spread that light into spectra, a rainbow barcode that shows what these galaxies are made of. They're looking for the lines of carbon, oxygen, neon. The goal is to catch these infant galaxies in the act, to measure the metal content in galaxies from just 400 million years after the Big Bang. If they find that even these earliest galaxies are already enriched, that's a smoking gun. It tells us the universe learned complex chemistry in a heartbeat. That the first stars didn't just light up the darkness, they lit the fuse for everything that came after. The speed of galactic growth might not be written only in the laws of gravity or dark matter. It might be written in the periodic table by the first furnaces to ever burn in the cold of space. The universe's final secret is in its first moments. We've looked for answers in dark matter, in stars, in black holes, but maybe the answer was written before any of that, written at the instant of creation. That brings us to cosmic inflation. A fraction of a second after the Big Bang, the universe is thought to have gone through hyper-expansion. It ballooned from a subatomic speck to something vast, unbelievably fast. And this wasn't just expansion. It was like a cosmic printing press. It took the tiniest quantum jitters fluctuations in the newborn fabric of reality, and it stretched them. Blew them up from the quantum scale to the cosmic scale. Those stretched ripples became the seeds for all structure. The slight overdensities, places with a tiny bit more stuff, and the underdensities, places with a bit less. That pattern is the universe's birth certificate, and we have a picture of it, the cosmic microwave background, that ancient afterglow from when the universe became transparent. That snapshot, taken when the cosmos was 380,000 years old, shows these ripples frozen. It gives us a blueprint, what scientists call a power spectrum. It tells us how matter was distributed across different size scales at that early moment. Our standard models of inflation produce a very specific, very smooth blueprint. One that predicts a slow, steady build-up of structure. But what if the printing press had a quirk? Our view of the cosmic microwave background is like looking at a vast mural from a distance. We see the large-scale patterns perfectly, the sweeping mountains and valleys, but the finest details, the texture of the brushstrokes on the smallest scales, are blurry to our instruments. It's possible inflation wasn't perfectly uniform. There could have been slight variations in how those quantum fluctuations were amplified on the very smallest scales. Features in the inflation model or a running spectral index could have given an extra boost to tiny ripples. That would mean alongside the large-scale blueprint we see clearly, there was hidden fine print. A subtle enhancement of density on much smaller scales, and that changes everything for galaxy formation. If certain microscopic regions were born significantly denser than average, they got a colossal head start. From the very first instant, these overdense seeds had stronger gravity. They would begin collapsing into dark matter halos far earlier than typical regions. They wouldn't have to wait for gravity to slowly amplify tiny differences. The difference was already baked in. When the normal baryonic matter, the hydrogen and helium, finally decoupled from the radiation, it would have a much stronger, much earlier gravitational well to fall into. It's the difference between trying to grow a tree from a scattered seed on open ground and planting a sapling that's already a foot tall. The process is accelerated from step one. So the brilliant galaxies we see with the James Webb Space Telescope might not be cosmic overachievers. They might simply be the children of these privileged seeds. They grew from regions that won the cosmic lottery at the moment of inflation. Their frantic speed isn't a violation of the rules later on. It was a gift from the very first rules. The timing problem of galaxy formation pushes our questions back to a time we can never observe directly, to the first trillionth of a second. The solution might not be in changing the physics of dark matter or stars. It might be in rereading the fine print on the universe's explosive birth certificate, looking for the hidden clauses that set some regions on a fast track. Population 3 stars, these are the first stars. They're ghosts from the very beginning. We've never seen one. We probably never will. Their whole story is just a shadow in our math. A prediction: they had to be different. They were made only of hydrogen and helium, the raw stuff from the Big Bang. Without heavier elements to cool things down, a cloud of that pure gas couldn't split apart. It couldn't make lots of small pieces, so it made a few huge ones instead. A single cloud collapsing into one enormous furnace, a star with the mass of hundreds of suns. Its surface would be incredibly hot, pouring out ultraviolet light. Its core would burn through its fuel in just a couple million years. Our sun has been shining for over 4 billion years. A population 3 star lived and died in less time than it takes for mountains to rise. Their short, violent lives weren't quiet. They were the first acts of creative destruction. That intense ultraviolet radiation was a physical force. It blasted outward, stripping electrons from atoms in the hydrogen around it. That process, ionization, heated the gas. It created expanding bubbles of hot plasma, like a bubble rising in water but cosmic. The edge of that bubble is a shock front, a wall of pressure moving through the early universe. And as it moves, it gathers the cooler gas ahead of it, pushing it, compressing it into dense shells and filaments. Inside those shells, conditions change. The gas is packed tight, ready to collapse. So the radiation that destroyed the calm universe also built the cradles for the next stars. That's feedback. The first light didn't just signal birth, it built the nursery, and then they died. A star that massive has a cataclysmic end. Some might have exploded as supernova. Unimaginably powerful, far beyond anything we see now. Those explosions did more than scatter new metals. The blast wave itself, a sphere of debris moving at a fraction of light speed, would plow into the surrounding gas for thousands of light years. That collision is another trigger. It slams into gas pockets, crushing them, starting a cascade of collapses that lights up whole regions with new stars all at once. A chain reaction of starbirth from one detonation, but there's another path. Some of these massive stars might have skipped the supernova. Their cores, so heavy, might have collapsed straight down under their own gravity. No big explosion, just a sudden plunge into darkness. The result, a black hole seed, with the mass of dozens, maybe hundreds of suns, appearing almost instantly in a young dark matter halo. That's the ultimate shortcut. Instead of a galaxy slowly forming a black hole, the black hole is there from the start, a massive anchor of gravity, ready to pull in gas, power quasars, organize the construction around it. Population 3 stars are the wild card. Their properties are still theoretical, but if they were real and as extreme as we think, they weren't just the first lights. They were the chaotic midwives of the cosmos. Their radiation, their explosions, their silent collapses could have set the tempo for everything after. They could have taken the slow, patient blueprint of dark matter and gas and rewritten it in a frantic, brilliant rush. To solve the mystery of the fast galaxies, we might need to find the ghosts of the first stars. We've been missing something, a hidden force to explain that frantic speed. But maybe the answer is a whisper of energy woven right into space itself. A whisper we still feel around us, magnetic fields. Our own galaxy is threaded with them. They guide cosmic rays, they shape nebulae, they influence how gas clouds collapse into stars. They're part of the cosmic machinery, but where did they come from? Were they there from the beginning? That's one of the deepest unknowns. Some theories go back to the universe's first moments, to the seething energy of the Big Bang. As the cosmos expanded and cooled, it went through dramatic phase transitions, like steam condensing into water. Those violent shifts in the state of the universe could have generated ripples in spacetime itself, and those ripples might have twisted the primordial soup of particles, creating the faintest magnetic fields. These would be seed fields, incredibly weak, stretched across vast regions of the infant cosmos. At first, they'd seem insignificant, a ghost of a force compared to gravity. But in the delicate balance of the early universe, even a ghost can tip the scales. Think of a vast, still lake. A single tiny pebble dropped in creates ripples that travel outward, organizing the water's surface. A primordial magnetic field could have been that pebble. It would have provided a subtle sense of order in the chaotic gas. Now, how could something so weak have such a powerful effect? It comes down to how gas behaves. Gas falling into a dark matter halo doesn't fall straight in. It has angular momentum. It swirls like water going down a drain. That spin creates a barrier. It can prevent the gas from reaching the dense center where stars are born. It needs to lose that spin to shed that angular momentum. In later galaxies, this happens through turbulence and collisions. But in the smooth, early universe, the process could have been too slow. This is where the magnetic seed might have worked. A magnetic field, however weak, is not a passive thing. It's a tension, a series of invisible lines. As ionized gas moves across these lines, it gets tangled. The field acts like a brake, a cosmic friction. It can help the swirling gas lose its angular momentum much faster. It siphons that spin energy away, allowing the gas to flow inward more efficiently, right into the heart of the forming galaxy. Instead of a slow, stately accumulation, you get a focused, rapid delivery of fuel. But that's not all. Magnetic fields also provide pressure. They can support a cloud of gas against its own gravity, like an invisible scaffold. This could, in some cases, slow things down. But in the turbulent cauldron of a young protogalaxy, the opposite might happen. The fields can get twisted and amplified by the churning motions, like stretching a rubber band. In a remarkably short time, they could grow from a faint whisper to a powerful roar. And these amplified fields don't just sit there, they channel the chaos. They can funnel gas flows into dense, focused filaments. Imagine trying to pour sand onto a table. It spreads out. Now put a series of tubes on the table. The sand flows through the tubes, piling up in specific, concentrated spots. Magnetic fields could have acted as those cosmic tubes, guiding the raw material of the universe into dense, star-forming cores with incredible precision and speed. This adds a whole new layer of complexity to our models. Simulating the early universe with magnetic physics is a monumental task. It means tracking not just gravity and gas, but this invisible, dynamic web of force. Yet it opens a possibility. The frantic assembly of the first galaxies might not need a rewrite of gravity or dark matter alone. It might have been supercharged by a hidden architecture, a magnetic skeleton that was there from the first moments, guiding the gas, speeding its journey, focusing the storm of creation into brilliant, early light. The universe's first cities may have been built along invisible roads. There's a fossil record in the sky, not in stone. It's a subtle pattern, a rhythm in how galaxies are scattered. You can't see it looking at one galaxy. You have to step back, look at the universe as a whole, statistically, and you find galaxies aren't placed randomly. They show a slight tendency to be separated by a specific, enormous distance. That's not an accident, it's a cosmic echo, a sound wave frozen in time. From when the universe was a hot, opaque plasma, that's the Baryon acoustic oscillation. It's a powerful tool for understanding structure, and it might connect to our early galaxy mystery. To understand the echo, go back to that early plasma, a fluid of light and matter tightly coupled, and in any fluid you can have sound waves, pressure waves. In that soup, gravity was pulling, trying to make matter clump, but the radiation pressure the light was pushing back. That tug of war set the medium ringing. A region of higher density would collapse under gravity, pressure would build, then rebound, pushing material out in a spherical wave, traveling outward at a huge fraction of light speed. Then the universe cooled, atoms formed, the light decoupled from matter, the universe became transparent, and at that moment those sound waves stopped. Frozen in place, the wavefront became a spherical shell of matter, a subtle overdensity, like a ripple in a pond that freezes solid at a certain size. That preferred scale, the distance the sound wave traveled, is imprinted. It became a standard ruler, a cosmic yardstick, hundreds of millions of light years across. Later, when galaxies formed, they tended to form more in regions of higher density. So statistically, you find more galaxies separated by that frozen sound wave distance than by pure chance. It's a faint pattern in the cosmic web. We've measured it beautifully in the recent universe. It's a cornerstone, confirming expansion history and dark energy. But now there's a new question for the James Webb era. What does this pattern look like at the very beginning? When we map those impossibly early, brilliant galaxies from the cosmic dawn, do they show this same preferred scale? Or is their distribution fundamentally different? The answer is a direct test. If those infant galaxies are clustered with the same Baryon acoustic oscillation signature we see later, it tells us something. It means the large-scale dark matter scaffolding the gravitational potential wells that seeded all structure was exactly as predicted. The underlying blueprint was correct. If that's true, then the problem of fast galaxy formation isn't with the cosmic architecture, not with dark matter's large-scale behavior. The issue must be local. With the baryonic physics, the ordinary matter, inside those halos, the gas cooled too efficiently, stars formed recklessly, black holes fed violently. The building materials behaved unexpectedly, but on a perfectly normal construction site. But what if the clustering is off? What if those early massive galaxies are more tightly clumped or more spread out than the standard model predicts? That would be seismic. It would suggest the initial conditions themselves were different. Maybe the primordial power spectrum, the blueprint of density variations from inflation, had more small-scale power, creating more numerous, closer-packed seeds from the start. Or it could point to the nature of dark matter. Warm dark matter suppresses small-scale structure. If early galaxies are less clustered on small scales than expected, it could be a signature of that faster, smoother dark matter. The spatial fingerprint of the first cities of stars becomes a diagnostic tool. It lets us distinguish between a universe where the rules are fine but the players are extraordinary, and a universe where the rules themselves need a rewrite. Making this measurement is a staggering challenge. It requires not just finding these faint, ancient galaxies, but mapping thousands across enormous volumes of the early universe. To build up the statistics, it requires exquisite precision to measure their redshifts, their three-dimensional positions. It's the ultimate cosmological census taken at the edge of time. But that's the power of the Baryon acoustic oscillation. It's a fossil imprint, a relic of the universe's first music. By listening for that same rhythm in the earliest galaxies, we can learn whether the cosmos sang the same song from the very first note, or if the opening bars were played in a different, more frantic key. The empty spaces between the first lights may tell us more about their origin than the lights themselves. Gravity is the oldest force we know, but it might be the least understood. Every explanation we have works inside the same framework, the one Einstein laid out over a century ago. But what if the framework itself is wrong, or at least incomplete for the conditions of the infant cosmos? That leads to a more radical proposal, one that questions the need for dark matter entirely. The idea is called modified Newtonian dynamics, MOND. It suggests our understanding of gravity breaks down under certain conditions, in regions of extremely weak gravity. Like the outer edges of galaxies, the force might behave differently than Newton or Einstein predicted. In these low acceleration environments, gravity could become stronger than expected. This simple tweak can explain why stars at the edges of spiral galaxies orbit just as fast as those near the center. A puzzle dark matter was invented to solve. It's an elegant alternative, replacing an invisible substance with a slight adjustment to the most familiar force. The challenge is scaling this idea up. And it is a monumental one, from explaining a single galaxy's rotation to explaining the entire universe's structure from the first moments. Some researchers are attempting that. Building relativistic extensions of MOND that could apply to cosmology. Could a modified gravity law have made the early universe clump together faster? Theoretically, yes. If gravity was effectively stronger on the vast, diffuse scales of the primordial cosmos, then those tiny density ripples would have grown into galaxies much more rapidly. The frantic speed of cosmic dawn could be a direct prediction, not a problem. It would mean we don't need warm dark matter or super-efficient stars to explain the timeline. The culprit would be gravity itself, playing by a different set of rules when the universe was young and sparse. This is considered a profound long shot by most of the scientific community. The reason is a mountain of evidence that seems to point unequivocally to dark matter's existence. Evidence a simple modification of gravity has struggled to address. Take the cosmic microwave background. That detailed snapshot of the infant universe shows a specific pattern of hot and cold spots. That pattern is exquisitely fit by a model. A model that includes cold dark matter and ordinary matter. A modified gravity theory must reproduce that perfect fit, and so far none have managed it as elegantly. Then there are observations of colliding galaxy clusters, like the Bullet cluster. When two clusters smash together, the hot gas, the ordinary matter, slows down and gets stuck in the middle. But something else keeps moving right through, something invisible. We can map it by how its gravity bends light from galaxies behind it. That map shows the mass is separated from the gas. This is interpreted as the dark matter, which doesn't interact with anything but gravity, so it simply sails through the collision. For a modified gravity theory to explain this, it would have to account for why the gravitational effect appears to be in a different place than all the visible matter. Without any invisible matter being there, it's a formidable hurdle, yet the severity of the early galaxy problem is like a persistent alarm. It's so loud that it encourages scientists to re-examine every single assumption. Even the most sacred, if all the solutions within the standard model start to feel like increasingly complex patches, then perhaps it's worth checking if the foundation has a crack. The pursuit of modified gravity in this context isn't about disproving dark matter outright. It's a stress test by pushing an alternative theory to its limits. By forcing it to explain everything from galaxy rotations to the cosmic microwave background to the frantic dawn, we learn something invaluable. Either the alternative theory breaks, revealing why dark matter is still the best answer, or it survives, and in doing so might reveal a deeper, more unified truth about how gravity actually works. The mystery of the universe's first galaxies isn't just pushing our telescopes to their limits. It's pushing our most fundamental ideas to the brink. Our models say a galaxy like the Milky Way should take about 1 billion years to form. That's the timeline, a slow build after the Big Bang, but the James Webb Telescope is seeing something else. It's finding galaxies just as massive, already shining, when the universe was only 300 or 400 million years old. That's not just faster, that's taking a billion-year process and squeezing it into a third of the time. Or less. This compression is the constraint now. It's the box every theory has to fit inside. Any explanation can't just be a little quicker. It has to be exponentially more efficient. It has to rewrite the rules. Think of building a cathedral. The old way takes generations. Now imagine building that same cathedral, just as solid, in a single season. You wouldn't just work faster, you'd need new materials, a whole new method, a different physics for building. That's why the answer probably isn't one thing. It can't just be warmer dark matter, or super-efficient stars, or hungry black holes alone. Each of those might shave some time off, but the discrepancy is so big it likely needs a combination. A cascade, a perfect storm. Picture a dark matter halo that forms earlier and more massive because of a tweak in its nature. Into that deeper well falls gas. But this gas is already a little warmed, pre-processed by the glow of the first stars, and it's already seeded with the first metals from those same explosions. So it cools and fragments with stunning efficiency. Stars ignite in a furious burst. Some collapse right into massive black hole seeds. Their feeding churns the gas, sparking more star formation. And this whole structure isn't alone. It's in a crowded neighborhood merging with other protogalaxies, violent acquisitions. Each collision triggers another wave. This isn't a linear line, it's a feedback loop. Faster halo growth enables faster gas collection. Faster gas collection enables faster star and black hole formation. Their explosive feedback reshapes the environment. It triggers even more efficient growth. It turns a slow cosmic simmer, where each step waits for the last, into a rapid rolling boil. Where everything happens at once, the early universe may not have had the luxury of patience. Its first structures might have been born in a frenzied, all-at-once rush. A cosmic shortcut where the normal rules of sequential development were bypassed entirely. Solving this means finding the recipe for that shortcut, understanding why the universe's childhood was so hurried. So brilliant, our view of the cosmic dawn is filtered through a lens, a powerful lens but a finite one. The James Webb Space Telescope is a marvel, but it has limits. Its sensitivity is incredible, but it's not infinite, and its observing time is precious. It's allocated to specific patches of sky that creates a bias. A fundamental bias in what we see. We're not getting a complete family portrait of the first galaxies. We're seeing only the ones that shout the loudest. The most brilliant, the most massive, the ones forming stars at a furious pace. It's like standing on a distant shore at night, looking toward a vast city. You don't see the quiet neighborhoods, you don't see the modest homes, the dimly lit streets. You see only the blazing skyscrapers downtown, lit up against the darkness. Those brilliant galaxies from 400 million years after the Big Bang, those are our cosmic skyscrapers. They dominate the view, but what about everything else? There could be vast numbers of fainter, smaller galaxies from that same time, more typical galaxies, galaxies growing at a slower pace, a more theoretical pace. They remain hidden, below the detection threshold of even our greatest telescope. That's the observational bias. It means our current sample, the one causing all the theoretical panic, might represent the extreme outliers. The prodigies, the freaks of nature, and if that's true, then the situation changes. The average timeline for galaxy formation in the early universe might still be slow. It might still be stately, just as our models predict. The frantic speed we're measuring wouldn't be the rule, it would be the exception, the spectacular exception. Now, this isn't to dismiss the discovery. Outliers are important. They test the limits of physics. They show us what's possible, but they don't necessarily show us what's typical. The critical task now is to push deeper, to stare longer, to use future cycles of the James Webb Space Telescope to conduct ultra-deep surveys, to peer into the same patch of sky for hundreds of hours, to tease out the faintest possible glimmers, and we have to look forward to the next generation of instruments, giant ground-based telescopes, mirrors over 30 meters across, equipped with even more sensitive infrared eyes. Their goal will be to take a true census, to count not just the brilliant downtown cores but the surrounding suburbs, the towns of the infant cosmos. Are those speedy, massive galaxies one in a million, or are they simply the brightest members of a vast, fast-forming population? Are they lonely skyscrapers, or are they the tips of a submerged mountain range? Answering that question is essential. It calibrates the true scale of the challenge. If they're rare, our theories might need only a slight adjustment. An adjustment to account for rare conditions. If they're common, then our theories require a rewrite, a foundational rewrite. The light we see is only part of the story. The darkness holds the rest. The universe started in a kind of fog, a dark age with space filled by this neutral hydrogen gas. It was thick and it blocked the light. That fog didn't just go away, it was burned off by the first bright objects. This whole period is called reionization. It's when the universe became transparent. When light could finally travel. For a long time, we've used the most distant quasars as probes, ancient, brilliant black holes. By looking at their light, we can see when the last of that hydrogen fog cleared. The evidence says reionization was mostly done when the universe was about 1 billion years old. That timeline went into our models. It told us how many ionizing photons were needed, how much ultraviolet radiation. It set a budget. The first stars and galaxies had to produce enough light over enough time to meet it. But now we have these galaxies. From just 400 million years after the Big Bang, impossibly bright, massive, that whole budget is in question. These aren't small candles, they're blazing beacons. Each one would have been a factory, pouring out ultraviolet light that strips electrons from hydrogen. If the early universe had many objects like this, then reionization didn't have to be slow. It could have been rapid, a furious firestorm. The fog could have cleared centuries earlier than we thought. This creates a link between two mysteries. We need those early, brilliant galaxies to explain how reionization happened so completely. Their luminosity is the missing power source, but the fact that reionization happened by a certain time also sets a limit. A constraint on how many such brilliant galaxies could have existed. We can't have so many that they over-ionize the universe too early. That would mismatch other observations like the cosmic microwave background. It's a balancing act. These frantic galaxies solve one piece of the puzzle, but they risk breaking another. So now we have to ask not just how fast galaxies formed, but what kind of light they made. Were their stars especially efficient at producing the hard ultraviolet photons needed to ionize hydrogen? Did their black holes contribute a significant part of this radiation? The answers reshape the whole timeline. The light that ended the Dark Ages may not have been a gentle sunrise. It may have been a sudden flash, ignited by galaxies that assembled themselves at a breakneck pace. A pace we are only now starting to measure. Solving the mystery of their speed is now tied to understanding the transparency of the cosmos. We see the universe through just one window. Those deep fields from the James Webb Telescope, they're not a full picture of the early cosmos. They're deep, but they're specific. It's like taking one ice core sample in Antarctica. From that single core, you can learn amazing things about Earth's past climate. But you can't know if that one sample represents the entire continent. You might have drilled into a unique place. That's the challenge, cosmic variance. The universe isn't perfectly smooth. On the largest scales, matter forms a web. Filaments, walls, huge voids, different volumes of space can have different average densities. Some regions are busier, richer in galaxies, others are emptier. This isn't a mistake, it's a fundamental feature. Structure grew from those initial quantum seeds. The problem is, we live in one spot, we look out from it. When we point our most powerful telescope at a random patch of sky, we're sampling one specific volume of the universe's history, and by pure chance, that volume might be special. It might be an overdensity, a cosmic metropolis in the making, even back at the dawn. In a region like that, conditions for galaxy formation would have been primed from the start. The gravitational wells deeper, the gas more abundant, collisions between proto-galaxies more frequent. Everything would happen faster, brighter, more dramatically than in an average, quieter part of the young cosmos. So those breathtaking galaxies we see in the first deep fields, the ones defying predictions, they might not be the norm. They might be the outliers, the privileged residents of an unusually rich neighborhood out at the edge of time. If that's true, the implications are enormous. It means we might be overestimating the universe's frantic pace. We'd be taking the extraordinary growth rate of one precocious cosmic city and applying it to the whole universe. Our core cosmological models might not be broken. They might just be misinformed by a spectacular but unrepresentative data point. The way to test this is with more windows. We need a cosmic census, not a single portrait. That's the next phase for Webb and future observatories, moving from deep, narrow fields to wide, panoramic surveys. To look at many different patches of the early sky scattered around, to count the brilliant galaxies in each one. If those impossibly early, massive galaxies appear in every single field at roughly the same abundance, then cosmic variance is ruled out. The frantic speed is a universal truth, a feature of the cosmos itself, but if they appear only in some fields and are absent in others, then we have our answer. The mystery was one of perspective, a universe that's lumpy, even in its infancy, giving us a biased first glimpse. The quest to understand the universe's childhood now hinges on this question of statistics. On moving from the singular, stunning discovery to the broad, contextual truth, the light we've seen is undeniable, but what it represents, a revolution in physics, or just a lucky glance into the universe's most vibrant early district, that remains to be seen. Chaos could have been the architect. Turbulence is something we know from the galaxies around us now. It's that churning motion inside giant gas clouds, stirred up by supernova explosions and stellar winds. That chaos creates pressure. It's like a constant internal storm that holds a cloud up against its own weight. It acts as a brake, a regulator for star formation, so only small, dense pockets collapse at a time. It's why our own galaxy makes stars slowly, at a sustainable pace. But the early universe was a different physical realm. The rules weren't the same. There were no previous generations of stars to explode and stir things up. No magnetic fields yet to channel the flows. No heavy elements to help the gas cool and settle. So when those vast rivers of pristine hydrogen and helium first flowed into the gravitational wells of dark matter halos, it happened with a raw, untamed violence. The infall was likely supersonic. Gas slammed into gas at speeds far faster than sound could travel through it. This wasn't a gentle settling, it was a catastrophic collision. Think of a perfectly still pond. You drop a single pebble and you get orderly, expanding rings. Now imagine a torrential downpour, thousands of heavy stones pounding the surface all at once. The water doesn't ripple, it froths. It becomes a seething, chaotic foam of intersecting waves and collisions. That froth is what primordial turbulence might have looked like. These supersonic flows created a labyrinth of intersecting shock waves. A shock wave is a wall of pressure, a sudden, violent boundary, and where these walls crossed, they did something extraordinary. They trapped gas, they squeezed it into dense, narrow sheets and long, thin filaments at their intersections. In an instant, vast volumes of diffuse gas were processed into a complex, high-density web. That changes the entire equation for star birth. For a cloud to collapse into a star, gravity has to win over internal pressure. In a smooth, quiet cloud, that's a slow battle. But in this turbulent web, gravity was handed a gift. The gas was already pre-compressed, squeezed into dense knots and strands by the shocks. The hard work of gathering material was done not by gravity over millions of years, but by hydrodynamics in a cosmic flash. In these pre-made high-density regions, gravity's job became almost trivial. It could quickly overwhelm the thermal pressure and trigger collapse, and crucially, it could trigger many collapses at once. Across the entire volume of a young protogalaxy, hundreds, thousands of these dense nodes could reach the tipping point simultaneously. Instead of a single, slow-forming stellar nursery at the galaxy's core, the whole structure would light up. Like a field of fireflies igniting in unison, star formation wouldn't be a centralized, regulated process. It would be a galaxy-wide frenzy, a starburst of unprecedented scale, built into the very physics of the gas's arrival. This turbulent catalyst offers a pathway, a way to get to the frantic masses we observe. A galaxy could build a significant portion of its stellar mass not in a slow, billion-year trickle, but in one explosive, chaotic burst right at the beginning of its life. The brilliant galaxies seen by the James Webb Space Telescope, then, might not be anomalies. They might be the natural outcome of a universe where the first gas flows were not orderly rivers but supersonic waterfalls, crashing down into dark matter bowls and churning themselves into a star-forming froth. The silence of the cosmic dawn may have been shattered not by a single clear note, but by a deafening, chaotic symphony of creation. The standard picture of feedback is control, like a thermostat. In a modern galaxy, when stars form, the biggest ones explode quickly. Their blasts and radiation heat the gas around them. They push it away, and that starves the galaxy. It can't make more stars. It's a self-regulating cycle. It stops a galaxy from using all its gas at once. It gives it a long, stable life. We thought this was a universal rule, a law, but the early universe was a different place. The rules weren't written yet. In that environment, feedback might not have been a brake. It might have been an accelerator, a turbocharger. Think about a supernova now. It explodes into space that's already been churned up. The shockwave expands into relative emptiness. It dissipates. It just pushes gas around. Now put that same supernova at the very beginning, inside a young, pristine dark matter halo. The gas there isn't diffuse. It's incredibly dense. It's still pouring in from the cosmic web. It's a thick, cold soup. When the shockwave from that first explosion moves outward, it doesn't hit a void. It slams into a wall of oncoming material. The collision is huge. The shockwave doesn't dissipate. It stalls. It piles up. It acts less like a wind and more like a snowplow. It gathers the gas ahead of it into a dense, cool shell. And inside that compressed shell, gravity finds its moment. The density goes past the critical point. The whole shell fragments. It collapses not into one new star, but hundreds, thousands, all at once. The explosion didn't end star formation. It triggered a second generation. More intense, radiation plays a similar role. The fierce ultraviolet light from those first massive stars doesn't just ionize gas, it creates sharp boundaries. Ionization fronts, like a flame moving through dry grass. This front races outward, but ahead of it, the neutral hydrogen gas isn't just sitting there. The pressure from the advancing light physically pushes the gas. It sweeps it up into a dense, cool layer right ahead of the burning front. And again, this layer becomes unstable. Gravitationally unstable, it fragments. It births new stars right at the edge of the destructive radiation. The act of destruction becomes the architect of creation. This is the flip from negative feedback to positive feedback. Instead of a thermostat, it's a chain reaction. One stellar generation lives and dies. And in its death, it doesn't clear the nursery. It prepares the nursery. It tills the soil. It plants the seeds for the next generation with a violence that ensures a more abundant harvest. The cycle feeds itself. More stars mean more supernova. More supernova mean more compression, more triggered star formation. The galaxy isn't regulating its growth. It's experiencing a runaway starburst, a frenzy, where almost all of its primordial gas gets converted into stars in a single, frantic epoch. This turns our standard wisdom on its head. We thought galaxies learned balance. We thought they evolved mechanisms to pace themselves, but the first galaxies might have known no such restraint. Their story wasn't careful cultivation. It was explosive, exponential growth. A fire that, once lit, found endless fuel in its own ashes. The brilliant galaxies we see at the dawn might not be monuments to slow construction. They could be the frozen aftermath of a chain reaction, a single spark that ignited the entire cosmic forge. There's this really strange idea out there. A dark star, it's not a star, not really, but it would look like one, a point of light like a sun. Only its power source would be completely different. It wouldn't run on nuclear fusion, not like our sun, not like any normal star. Instead, it would be powered by dark matter. The idea depends on a specific kind of dark matter. Particles that can annihilate. When one meets its opposite, they destroy each other. That mass becomes energy. We see that with ordinary matter. This theory says dark matter could do the same thing. So you have to picture the beginning, those first clouds of gas, hydrogen, helium, and according to this, packed with dark matter. As the gas collapses under gravity, it pulls the dark matter down into the center, into the core, and there the particles annihilate in huge numbers. That process releases heat, a tremendous amount of heat. That heat creates pressure. Outward pressure, it pushes back against gravity. The whole thing stabilizes, it shines, but the light comes from that dark matter engine. A star like that wouldn't have the same limits. It could become enormous, millions of times the mass of our sun. It could shine for millions of years, steady, bright, and it would never ignite fusion. It would be a phantom, an illusion. From far away, it would just look like a galaxy. An incredibly bright early galaxy, or the core of one. That's the kind of idea the Webb data pushes you toward. A dark star could explain those puzzling bright objects. Their brightness wouldn't need frantic star formation, wouldn't need a supermassive black hole. It would be a different physics, and then it ends. Eventually the dark matter in the core runs out. The annihilation stops, the heat fades. Without that pressure, the whole structure collapses. It falls in on itself. In that collapse, it could form a black hole seed, an immense one, a direct path to the giant black holes we also see early on. The dark star idea is out there. It's speculative, pure theory. There's no evidence for it, just the need to explain what we're seeing, but it's important. With a mystery this big, you have to consider everything, no matter how strange. The early universe was a place for physics we can barely picture. The answer to its speed might not be in the stars we know. It might be in the shadows. We build universes inside computers. They're models, not mirrors. Every simulation is a compromise. You have to simplify a reality that's too vast, too intricate to capture perfectly. Even the most powerful supercomputers can't calculate the fate of every atom from the Big Bang to now. They work by dividing the cosmos into a grid, a three-dimensional mesh of points. They calculate the physics at each point: gravity, gas pressure, expansion, but the grid has limits. Its resolution is finite. It's like trying to paint the Mona Lisa with tiles the size of your hand. You get the overall composition, the smile, the background, but you miss the brushstrokes, the play of light in the eyes, the texture that gives it life. Cosmological simulations have that same limitation. They paint the large-scale cosmic web beautifully, the sweep of dark matter filaments over billions of light years. But inside each massive tile of that grid, an entire galaxy is born and dies. The grid can't see the individual stars. It can't trace magnetic fields being twisted by newborn suns. It can't follow radiation carving through clouds of gas. All that small-scale chaos happens below the grid. It's sub-grid physics, and since we can't compute it directly, we give the computer a recipe. A set of simplified rules based on what we see in the universe now. We tell it when gas in a grid cell reaches a certain density, convert some percentage into stars. We tell it when stars form, inject this much energy back for supernova. These recipes work well for building a universe that looks like our local neighborhood. But they're built from observations of mature galaxies, metal-rich galaxies. They're rules written for a cosmos that's settled into a kind of middle age. What if the infant universe used a different cookbook? What if, without metals and dust, the conversion of gas into stars wasn't a cautious process of a few percent, but a voracious, near-total consumption? Our simulations using modern recipes would never make that leap. They'd apply the brakes of feedback, slowing growth to a stately pace, while the real early universe was flooring the accelerator. The same goes for radiation. The light from the first stars was pure, hard ultraviolet pouring into a neutral medium. How that radiation propagated, how it heated gas, how it created ionization fronts that triggered new collapse, that's a fiendishly complex web. Our models use approximations here too, but if those approximations are even slightly off for those extreme conditions, you get a universe that wakes up too slowly. The brilliant galaxies seen by James Webb would be impossible in the simulation's cautious reality, so the tension is profound. It creates a fork in the road. One path says our fundamental cosmology is wrong. We have to change dark matter or even gravity itself. The other path, maybe more humbling, says our cosmology is right, but our understanding of the ordinary matter within it, the baryonic physics, is still primitive. We haven't learned to write the true recipes for creation's first frantic moments. The challenge for the next decade isn't just bigger telescopes, it's building better universes inside our machines. That means simulations with immense resolution, so they can begin to model those sub-grid processes directly. It means running ensembles of virtual cosmos, each with slightly different recipes for star formation, feedback, magnetic fields, to see which one, when fast-forwarded 13.8 billion years, produces a dawn filled with impossibly bright young giants. The digital universe is our laboratory. Its failure to match reality isn't a crisis. It's the most precise instruction manual we have. It tells us, line by line, which approximations to question, which physical processes we need to see in finer detail. The answer to the universe's hurried childhood may not be in new laws, but in the overwhelming, beautiful complexity of the laws we already have. Light tells a story, but it's a biased story. It scatters off dust, it gets absorbed by gas, it can bend and blur on its way to us. For decades, our whole picture of the cosmos came from this one fragile medium. But the universe speaks in more than light. It hums with vibrations, it whispers with ghostly particles. To really solve the mystery of the cosmic dawn, we have to listen to these other voices. That's the promise of multi-messenger astronomy, a future where we perceive the cosmos through all its senses. Gravitational waves are one of those new senses. Ripples in the fabric of spacetime itself. Einstein predicted them, and we finally detected them just a few years ago. When massive objects like black holes spiral together and merge, they don't just flash with light. They shake the universe, they send out a tremor that travels at the speed of light, unhindered by gas or dust. Now imagine detecting a chorus of these tremors from the very edge of time. A population of gravitational wave signals from mergers of black holes billions of times the mass of our Sun, coming from when the universe was just a few 100 million years old. That would be a smoking gun. It would tell us directly that supermassive black holes were not only present in the infant cosmos, they were already grown, already colliding in a crowded, violent nursery. Such a signal would be the most direct evidence possible for that frantic, accelerated timeline we're glimpsing with light. Future space-based observatories are being designed for this exact goal, to tune into the low-frequency hum of these ancient, colossal collisions. Then there are neutrinos. The universe's ghost particles, trillions pass through your body every second, leaving no trace. They're produced in staggering numbers by the violent deaths of massive stars. In supernova explosions, every star that died in the early universe, in those frantic first bursts of creation, sent out a pulse of these nearly massless, chargeless particles. Over billions of years, those pulses have blended together into a diffuse cosmic background, a faint, omnipresent sea of neutrinos that holds the integrated history of all stellar death. If we could one day detect this background, it would be like taking a direct census. We could count, in a way, how many stars lived and died in that first furious epoch. It would give us a number, a constraint independent of the tricky interpretations of ancient light. Did star formation happen in a slow trickle or in a sudden, overwhelming flood? The neutrino background would hold the answer, pristine and unaltered from its journey across time. These messengers, gravitational waves and neutrinos, carry information that light simply cannot. Light shows us the aftermath, the glowing embers of events, but gravitational waves show us the event itself, the raw dynamics of gravity in its most extreme state. Neutrinos offer a ledger, a sum total of stellar activity that no telescope can ever fully tally. They bypass the cosmic fog, the dust, the confounding brilliance of later generations. They offer a clear channel back to the chaos of the beginning. Of course, detecting these signals from the cosmic dawn is a monumental challenge. They are whispers against a roar of modern cosmic noise. But the planning is already deep underway. International collaborations are designing the next generation of instruments, both in space and deep underground. With a sensitivity to reach back to those first chapters, the full solution to the early galaxy mystery may not come from a single brilliant image. It may arrive as a subtle tremor in a laser beam, or as a rare flicker in a vast tank of ultra-pure water buried under a mountain. To understand the universe's frantic childhood, we must become more than observers. We must become listeners, feeling for the vibrations and tracing the ghosts of a dawn written in a language far older than light. This search for the universe's first moments. It's more than a technical puzzle. It touches something deeper. For as long as we've looked up, we've told stories about where it all began. Ancient cultures had their tales. God's primordial waters, cosmic eggs, world trees. These were the first models, attempts to put a narrative on the chaos of existence. Then modern cosmology gave us a new story. Written in mathematics, observed in light, the lambda cold dark matter model was the masterpiece, a single, elegant framework. It could trace the universe's journey from a hot, dense point to the vast, structured cosmos we see now. It felt complete, authoritative, a story we thought we had largely finished. Then the James Webb Space Telescope sees these brilliant, impossibly early galaxies. It's like finding a forgotten chapter in that book, a chapter that changes the meaning of everything after. It suggests the prologue wasn't a slow, stately overture. It was a frantic, explosive opening act that carries a profound weight. It's a humbling reminder. Science isn't a vault of settled truths. It's a living process. Successive approximation. We build the best model we can with the light we have. Then a new window opens, and we see our model, for all its beauty, is incomplete. The universe can still surprise us. This potential revision challenges a quiet assumption in our science, the principle of uniformitarianism, the idea that the physical laws governing the cosmos today are the same laws that have always operated. But what if, in the extreme densities of the first few 100 million years, the rules were subtly different, not broken but bent? Maybe dark matter behaved in a novel way when it was the dominant force. Maybe gravity itself had a different character in that nearly uniform sea of primordial gas. Or maybe the rules were the same, but the initial conditions, the blueprint from the first instant, were far more potent than we ever measured. Either possibility reshapes cosmic history. It suggests the universe's childhood wasn't just a smaller, hotter version of its adulthood. It was a distinct epoch, operating under a unique set of pressures and possibilities. That has startling implications for one of our deepest questions: are we alone? If galaxies and stars assembled with this breakneck speed, then the cosmic clock for life may have started ticking far earlier. The first rocky planets could have formed around stars that shone when the universe was less than 1 billion years old. That adds billions of extra years. For chemistry to become biology, for life to arise, evolve, and maybe even look back at the cosmos with its own wonder. Our own civilization, appearing roughly 13.8 billion years after the Big Bang, might not be an early arrival. We could be latecomers to a party that started in the universe's frantic youth. This isn't just adjusting a timeline in a textbook, it's a potential paradigm shift in our understanding of cosmic evolution, and by extension, our place within it. The story we tell about the universe's origins is fundamentally a story about our own. To rewrite that first chapter is to reconsider the entire narrative of how complexity and perhaps consciousness finds a foothold in the void. So this quest to understand these early galaxies, it's more than astrophysics. It's the latest chapter in humanity's oldest story, the story of where we came from and what the night sky is trying to tell us about our home in time. The next decade is going to be a golden age for cosmic archaeology. We're not waiting for one answer. We're building an armada of new eyes. The James Webb Space Telescope will keep doing its deep, patient stares. But its work will be amplified by a fleet of next-generation observatories. Each one is designed to look at a different piece of this ancient mystery. The Nancy Grace Roman Space Telescope, launching in 2027, is the wide-angle surveyor. Webb looks at postage stamps of the sky in incredible depth. Roman will take panoramic portraits. It will scan huge volumes of the early universe. It will find not just the brilliant downtown cores of the first cities, but map their suburbs and outskirts. This gives us the statistics we need. It tells us if those frantic early galaxies are rare freaks of nature or the typical residents of the cosmic dawn. By measuring how they cluster together across space, Roman's data will test something directly. It will test whether we've been fooled by cosmic variance by looking at an unusually rich neighborhood, or if the entire infant universe was indeed this crowded and bright. On the ground, a new generation of giants is rising. The extremely large telescope and the giant Magellan telescope are engineering marvels. Their primary mirrors, stitched together from segments or cast as single pieces, will gather light with a collecting area far beyond any current ground-based telescope. But their true power isn't just their size, it's their instruments. They will perform high-resolution spectroscopy on the faint, reddened light from these primordial galaxies. Think of spectroscopy not as a picture, but as a forensic analysis. It spreads the light into a rainbow barcode. From that barcode, astronomers can read the galaxy's vital signs. They can measure the precise motions of its gas, revealing if it's a calm disk or a turbulent, merger-driven mess. They can detect the chemical fingerprints of elements like carbon, oxygen, and neon. Finding these metals in galaxies from just 400 million years after the Big Bang would be the smoking gun. It would prove the first stars polluted the cosmos with heavy elements almost instantly, supercharging everything that followed. These telescopes will also pin down redshifts with exquisite precision, removing any lingering doubt about the true distances to these objects. Meanwhile, a different kind of eye will tune into a different signal. The square-kilometer array is not an optical telescope. It's a vast radio observatory with thousands of antennas spread across continents. Its mission is to map the universe in radio waves, specifically targeting the faint emission from neutral hydrogen gas. This is the raw material of the cosmos. The SKA aims to create a three-dimensional map of this hydrogen during the epoch of reionization. It will show us the cosmic web of gas before the galaxies lit up, and then trace how that web was carved apart and ionized by the first brilliant objects. It will show us the environment. Were early galaxies surrounded by vast reservoirs of pristine fuel, or were they islands in an already ionized sea? This map provides the crucial context, the nursery itself against which the story of the first galaxies unfolds. This coordinated multi-wavelength campaign is the key. No single telescope can solve this puzzle. We need Webb's infrared sensitivity to find the galaxies. We need Raman's wide field statistics to count them properly. We need the giant ground-based telescopes to perform their chemical autopsies. And we need the SKA to map the primordial gas they grew from. Together, this fleet will gather a dataset of unprecedented richness. It will allow us to run a cosmic test. We will feed this torrent of new data into our most sophisticated supercomputer simulations. And we will see, finally, which theoretical pathway leads to a virtual universe that looks exactly like the one we observe. Do the simulations need warmer dark matter to match the observed clustering? Do they need super-efficient, metal-free star formation to explain the chemistry? Do they need primordial magnetic fields to explain the gas dynamics? The data will rule theories in or out with a clarity we have never possessed. We are on the cusp of moving from a state of thrilling confusion to one of foundational understanding. The next 2 decades will transform a collection of shocking anomalies into a new, coherent chapter in the story of our cosmos. The mystery of the universe's frantic childhood is not a dead end. It's a signpost pointing the way to the next great discovery. The number of possible answers is important. It tells us no one change to our models is enough on its own. To build a cathedral in a season, you don't just need faster bricklayers. You need a new plan, stronger mortar, a team working in perfect, frantic sync. The early universe might have worked on that principle. That frantic speed could be several extraordinary conditions all aligning at once, a sequence that's not separate events, but a chain reaction. It starts with the cosmic scaffolding. Maybe dark matter was slightly warmer or self-interacting. That would let massive dark matter halos form earlier. With denser cores, these aren't the faint, wispy bowls from the old simulations. They're deep, steep-walled wells, carved into space much sooner. Into these early wells flows the primordial gas. But this gas isn't calm and cold like we once thought. It's been preheated by the glow of the very first stars or even by leftover energy from the Big Bang. It's warmer, more ionized, already laced with the first heavy elements, the ashes from those short-lived population 3 stars. That pre-processing is critical. The gas doesn't start from scratch. It arrives primed for collapse, its cooling efficiency supercharged by those first traces of carbon and oxygen. Then the engines ignite. Inside these deep, gas-rich halos, star formation doesn't proceed at a cautious pace. It erupts. The first generation of monstrous stars lives and dies in a flash. But their deaths aren't an end. Their supernova do 2 things at once. They blast the surrounding medium with metals, enriching it for the next wave. and their shockwaves plow through the dense gas, not blowing it away but crushing it into dense shells, shells that immediately fragment into the next generation of stars. That's positive feedback on a galactic scale, explosions that build rather than destroy. Amidst this firestorm, another player emerges. In the chaotic core, direct collapse black holes may form. Or the remnants of the most massive stars collapse into hefty seeds. These black holes aren't passive. They're active, feeding anchors of gravity. Their fierce radiation and powerful jets act like a cosmic piston. They churn the gas, adding turbulence and pressure, which can further compress gas clouds and trigger even more star formation around them. The black hole and the stellar nursery aren't in competition. They're partners in a frenzied dance, each fueling the other's growth. Then consider the environment. This whole drama isn't playing out in an isolated void. The early universe was crowded, bustling. These rapidly growing proto-galaxies are jostling neighbors, frequently merging and colliding, a violent game of gravitational acquisition. Each major merger sends another shockwave through the combined gas, setting off yet another super starburst, building mass not just from within, but from without. When you combine these factors, premature halos, pre-processed gas, explosive stellar feedback, active black holes, and frequent mergers, you don't just add their effects. You multiply them. Each factor makes the others more potent. Efficient star formation enriches the gas faster, which makes future star formation even more efficient. Black hole growth stirs the pot, making stellar birth more violent. Mergers deliver fresh fuel and trigger new bursts. The system enters a state of runaway growth. A virtuous cycle of creation. It compresses billions of years of theoretical development into a few 100 million years of real history. This is the new frontier for theoretical cosmology. The goal isn't to find the one magical ingredient anymore. It's to find the precise recipe, the right combination and sequence of these physical processes. So when you plug them into a supercomputer simulation, it spontaneously gives birth to a virtual universe, one whose first deep field images look exactly like the stunning, puzzling panoramas we're getting from the James Webb Space Telescope. We're moving from a list of possibilities to the hard work of synthesis, to building a new, unified model of cosmic dawn, one that explains not just that the universe was in a hurry, but precisely how it orchestrated that rush. The answer was never going to be simple. It was a symphony played in the dark by an orchestra of forces we are only now beginning to hear. This discovery goes beyond a puzzle. It's an opportunity, a chance to question what we thought we knew about the early universe. For a long time, our models felt settled, like a story whose opening chapter was understood. Now we have a new page, a contradictory one, and that's what scientific progress is. It's not confirming old ideas, it's the shock of the new, that tension between what we predict and what we see. That's the engine. It forces us to innovate, to imagine, to build tools that see farther. The answer might be in dark matter, or the physics of the first stars, or a combination of factors. But one thing is clear, this is a pivotal moment. The foundational story of everything is being rewritten. Right now, this mystery shows something. The universe is more inventive than our best ideas. Our theories are maps drawn from the light we can see, but the cosmos is the territory, vast and wild, full of things we haven't named yet. Those frantic early galaxies remind us. We're not the authors of this story, we're the students, the detectives, piecing together clues from the edge of time. We stand on the work of giants. The ones who built Hubble and the pioneers of deep field astronomy. Now, with the James Webb Space Telescope and what comes next, we're not just reading that first chapter. We're rewriting it line by line. This is a human endeavor, a testament to curiosity. So consider this journey. What does a faster-forming universe mean for cosmic time? For the architecture of reality, for our own origins in this story, The conversation is starting.